All right, in this next video in section 13.4, we're going to look at problem number 4. And this question says, level curves for a function f are shown below. The numbers next to each curve indicate the altitude. Determine whether each derivative is positive, negative, or 0. Okay, so when they say the numbers next to each curve indicate the altitude, what they're saying there is that if I take one of these level curves, like let's say this line labeled with a 9, that's just saying that this consists of all points up on our surface that are at the altitude of 9. Okay, and so notice here this altitude is going up by 2 as we go in the positive y direction. So it goes from 5 to 7 to 9, then this would be 11, 13, so on and so forth. Okay, so let's look at part A. This is the x derivative of our function evaluated at p, and our job is just to determine whether this is a positive, negative, or 0 value. Okay, so here we are at p, and what we want to do is walk in the positive x direction. And really what I want to determine is for fx, right, is my hillside going to be sloping upwards or sloping downwards? Or put another way, is my altitude increasing or decreasing as I move in the positive x direction? Okay, so here I can see I'm going from an altitude of 7 down, right, towards the altitude of 5, or put another way, if I draw a little cross-sectional view here, little xz cross-section, at the point P, okay, my altitude is 7, and then walking in the positive x direction, since my altitude's going down to an altitude of, say, 5, my cross-sectional curve here looks something sort of like this. Okay, and what fx measures is just measuring the slope of our surface, or equivalently the slope of this tangent to this cross-sectional curve at P. So m here, which would be our x derivative at P, would be, in this case, negative, right? We're decreasing in the positive x direction. So our answer here would be that fx at P is a negative value. Okay, now for part B, really the same kind of thing here. We're going to now move in the positive y direction. And here we can see, right, our altitude now is increasing. We're going from an altitude of 7 up to an altitude of 9. And again, in terms of the cross-sectional view, we'd now be looking at a YZ cross-section. Our altitude at P is 7, and then we're moving towards a contour at an altitude of 9, right? So we're going to be moving up like this, and since Fy is just measuring the slope of our surface in the positive y direction, this would be a positive value. All right, great. So our answer here is that Fy at P is positive. Okay, so that's for our first order derivatives. So now looking at parts C and D, these are second order derivatives. So for C, it's the fxx derivative at P, which we've defined to just be the x derivative of the x derivative of our function f evaluated at P. Okay, now in the last video, right, we said, well, this is just measuring how our slope in the x direction changes as we move in the positive x direction, and that's equivalent to just asking about the concavity of our surface in the x direction. So I'll go ahead and draw another cross-sectional view down here. And so what we said up in part A, right, we said, okay, well, at P, our altitude is 7, and then moving forward in the positive x direction, we're moving towards an altitude of 5, So the big question is, right, how exactly are we decreasing, right? Are we decreasing in a concave up way, a concave down way, in a linear fashion, right? What exactly is going on there? So that really is going to be determined by the spacing of the contours, okay? So notice as I move from left to right, our spacing is increasing, right? Way off here to the left, these are really closely spaced contours. Way out here to the right, greater spacing. And what we said when we just introduced contour diagrams is we said for really, really closely spaced contours, we're going to see, right, greater changes, right, steeper hillsides, because we just don't have to move as far to achieve that same change in altitude, right? To go from, say, an altitude from 13 down to 11, I don't have to move very far away over here, and that's a change of 2 units, right, in the z direction. But then to go from, say, 7 down to 5, I have to cover this huge distance. So what is that saying about my hillside? It's saying, right, that it's becoming more mellow, right, as I move in the positive x direction. So if I'm going to come over here and draw a picture, I'm just mellowing out here, right? So if I were to measure again the slope here at P, and then I'd measure the slope again a little bit ahead, right? This slope in green is going to be more mellow than the slope here in blue. Or put another way, right, our slope is getting less negative. So that's going to tell us that the xx derivative is in fact positive, right? There's an increase in the values of the slopes there, right? Because we're getting less negative. And again, that aligns with what I'm saying here about concavity. We have a concave up shape for our cross section at P. Okay, cool. So second derivative there, the xx derivative is positive. So then lastly, this is going to bring us to the mixed partial fxy at P. Now again, with the subscript notation, this is really saying to do what? It's the x derivative first, you just go left to right, and then we're going to take the derivative of that thing with respect to y and evaluate at P. Or put another way, this would be the y derivative of the x derivative of our function evaluated at P. Okay, so now what I'm going to do is I'm going to look at our x slopes, which are these things, and then we're asking how are they going to change as I move in the positive y direction. So you can imagine standing here at P, we're going to measure the slope of our hillside in the positive x direction. Then what we're going to do is we're going to move up a little bit, say to this point, and then we're going to measure the slope again, right? Are we getting steeper, less steep, right? That's the kind of thing we want to determine, right? We want to know how these two slopes compare. Okay, so I'll come down here and draw a little cross-sectional view to help us think about this. So here is, say, one cross-sectional view. So here we are, say, at P, and we have this sort of concave up cross-section there. And we know the slope at P is this negative value. Okay, and so now what I want to do, right, is I want to take a little step in the positive y direction. So I'll say a little dy change in the y direction, and then what I'm going to do is look at this cross-sectional view and ask, right, am I going to be steeper or less steep up here as I move in the positive y direction? Well, notice again spacing, right? As I move in the positive y direction, the spacing is becoming tighter. So that's indicating what? It's indicating, right, that this cross-section would be steeper, right? Closer spacing, steeper the slope. So that's going to give me some cross-section that's going to look something maybe like this. and the slope at this corresponding point, say over here, is going to be steeper. Okay, so just to make this a bit more concrete, let's just make up a couple numbers here. Like let's say the slope here, so I'll call this the slope in the x direction at p. Let's say this is like say -2. Okay, then what we're doing is we're just marching over right a little bit in the positive y direction, and then we're going to measure the slope in the x direction again. And since right spacing is getting tighter, this is going to be right a greater, or sorry, it's a, well, it's greater in magnitude, but it's more negative, right? That's the way to say it. So it maybe is say something like -4. Okay, so what does the xy derivative really measure? It measures the change in these slopes, right? The rate at which this x slope is changing. Okay, so we would say this, something like mx2 minus mx1. Since this is a negative difference, right? -4 minus -2, that's a negative number, right? What that's telling us then is that the xy derivative, which is measuring the rate at which this slope is changing, is itself negative. Okay? All right, so a little more going on there with the mixed partial. Now we know from Clairaut's theorem that the yx derivative is going to equal the xy derivative. So it as well will be a negative value. But I encourage you to go through this kind of thought process to actually convince yourself of that fact, right? That if you did the yx derivative, so think about how do the slopes in the y direction change as we move in the positive x direction, right? That should still come out to be a negative value, all right? So that's going to do it for this problem. I'll see you next time.